Super Nintendo – Why raw power isn't always the answer. When Nintendo decided to create their new console, rather than focusing on raw power and the most high-tech, expensive components like its rival, the Sega Mega Drive, they took a divergent approach, aiming to deliver next-gen graphics and sound while keeping the console affordable. Additionally, they designed the SNES with expansion in mind, which proved to be a masterstroke as the world of CPUs was evolving faster than Bowser could kidnap Princess Peach. The heart. Delving into the heart of the Super Nintendo, its CPU choice wasn't the most high-end option available at the time, but it was a familiar, reliable workhorse. The Nintendo Entertainment System used a modified 6502 CPU, an influential component in the late 70s and early 80s computers. For the Super Nintendo, Nintendo decided to upgrade to the 65C816, a 16-bit extension of the 6502. Now, what's special about this 65C816 CPU? It originated from Western Design Center, a company founded by Bill Mensch, who was part of the original 6502 team. This CPU was chosen by Apple for a new machine called the Apple II GS. Around the same time, Nintendo was collaborating with Ricoh on custom chips for the NES. At some point, Western Design Center licensed the 65C816 design to Ricoh, which was then tailored to meet the Super Nintendo's needs, giving birth to the Ricoh 5A22. Interestingly, unlike the Apple II GS, the Super Nintendo was not compatible with NES games. However, the choice of CPU implies that there might have been initial plans for such compatibility. Who knows? The Ricoh 5A22 had a variable clock speed, reaching up to 3.58 MHz during register operations and dropping to 1.79 MHz when accessing the slowest buses. What truly differentiated the Super Nintendo was how Ricoh enhanced the 65C816 for the console. Firstly, they added 16-bit multiplication and division units, which facilitated more complex arithmetic operations. Secondly, they included 2 direct memory access units, allowing data to be moved swiftly without needing the CPU's intervention. The 2 DMAs served distinct functionalities. The general-purpose DMA could perform transfers at any time, while the horizontal DMA performed small transfers after each horizontal scan. This design prevented the CPU from being interrupted for long periods. The Super Nintendo also had a fascinating feature, the open bus. If an instruction tried to read from an invalid address, the last value read was supplied instead, and the execution carried on in an unpredictable state. The graphics. Now, let's talk about the real superstar of the Super Nintendo, the graphics. Nintendo and Ricoh engineers performed a magic trick with the graphics subsystem. Despite a constrained CPU, they managed to create stunning visuals that challenged its 32-bit competitors. To achieve this, the Super Nintendo used 2 different picture processing unit chips known collectively as the Super PPU or the SPPU. These chips worked together, rendering graphics and adding effects such as window, mosaic, and fades. The system even allowed for different modes that controlled the graphics' color, number of layers, effects, or resolution. The SNES had 2 custom-designed PPUs, PPU-1 and PPU-2, which worked in unison to handle the system's graphic output. Both chips were developed by Nintendo and Ricoh. PPU-1, also known as the SPPU-1, was responsible for the rendering of background layers. It had its own video RAM of 64 kilobytes for storing background tiles and sprites, and object attribute memory for sprite data. PPU-1 was able to produce up to 4 different background layers, depending on the graphic mode being used. This allowed for a deep sense of parallax and created more complex and visually appealing scenes. Additionally, PPU-1 was responsible for implementing the different graphic modes available in the SNES. These included 7 modes, Mode 0 to Mode 7, each with its own unique capabilities and limitations regarding the number of layers, colors, priority, and effects. Most notably, Mode 7 allowed for a single layer of 128 by 128, 256 by 256, 512 by 512, or 1024 by 1024 tiles that could be scaled and rotated. PPU2 or the SPPU2 handled sprites, color generation, and on-screen effects. It was also responsible for reading the data from VRAM and OAM to actually render the final picture that would be sent to the television screen. In terms of color handling, the SNES was able to show up to 256 colors on screen simultaneously, from a palette of 32,768 possible colors. This color depth combined with the layering capabilities of the PPU allowed the SNES to create rich, detailed, and vibrant graphics. While the PPUs had a clock speed of 5.58 MHz, they also had access to some special graphical effects, such as pixelation, mosaic, and transparency, that could be applied independently to sprites and background layers. This allowed for unique visual aesthetics and styles in games. Together, the PPU-1 and PPU-2 performed admirably, giving the SNES its unique graphical capabilities and setting it apart from its competitors. However, the PPU's real strength came not just from their individual capabilities, but from the way they worked together to manipulate and render graphics. The audio. What truly sets the Super Nintendo apart, however, is its sound. Partnering with Sony, Nintendo managed to create an advanced synthesizing system that included a digital signal processor and a CPU. This combo could sequence and mix samples, creating a vast range of sounds that elevated the gaming experience. The sound subsystem in the SNES was a powerful component that significantly contributed to the console's lasting appeal. Sony engineer Ken Kutaragi, who later played a key role in the development of the PlayStation, designed the subsystem. It included the Sony SPC700 sound processor, which operated independently of the console's main CPU, allowing it to generate complex audio without burdening the main system. The SPC700 ran at a speed of 1.024 MHz and was complemented by 64 kilobytes of SRAM, used for storing audio samples and other data. The SNES's sound system also included a digital signal processor for producing sound and performing tasks such as envelope height, noise generation, echo, and other effects. The SNES was capable of producing 8 channels of ADPCM encoded audio simultaneously, each of which could be panned left or right. This not only allowed for a rich array of sound effects, but also sophisticated music. The sound quality was such a leap forward from previous generation systems that it lent itself to the creation of some of the most memorable game soundtracks of all time. Composers had an unprecedented range of tools at their disposal, which gave rise to some of the most memorable video game music in history. Classic SNES games like The Legend of Zelda: A Link to the Past, Chrono Trigger, and Final Fantasy VI, or 3 in the US, are frequently lauded for their remarkable soundtracks. These impressive audio capabilities allowed the SNES to create immersive audio experiences, providing not just a visual, but also an aural sense of different gaming worlds. From the thump of Samus's footsteps in Super Metroid to the roar of Bowser's fire in Super Mario World, the SNES delivered an audio experience that added an additional layer of depth and immersion to games. The memory. Now that we've examined the CPU, the graphics, and the sound system, let's move on to another pivotal component of the Super Nintendo, the memory. The Ricoh 5A22 CPU had access to a complex memory setup. The CPU itself contained 128 bytes of direct page memory, a small amount of high-speed SRAM used for quick operations. Additionally, it had direct access to the 128 kilobytes of main system memory, called work RAM. The WRAM was shared between the CPU and the PPUs, thus they had to take turns accessing it, which was managed by an arbitration system. The memory setup was even more diverse when it came to cartridges. While cartridges of the era typically contained ROM, the Super Nintendo cartridges also had SRAM for game save data and sometimes even custom hardware such as the Super FX chip, used to produce polygonal 3D graphics. The console also boasted 64 kilobytes of video RAM that stored the tile and map data for the background layers as well as sprite patterns. It had an additional 512 bytes of object attribute memory to hold sprite parameters and 512 bytes of color generator RAM to store the color palette data. To communicate between these various components, the Super Nintendo employed a complex bus system. The bus design allowed for simultaneous data transfers between different components without stalling the CPU. One of the most fascinating aspects of the Super Nintendo was its ability to perform complex graphics operations with only a fraction of the processing power that modern consoles use. This was largely due to the unique Mode 7, a graphics mode that allowed a background layer to be rotated and scaled, creating a pseudo 3D effect. This feature was used to great effect in games like F-Zero and Super Mario Kart, giving players an impression of 3D gameplay on a 2D system. The Super Nintendo Entertainment System was a marvel of engineering and design. Its custom chips, unique graphics modes, and advanced sound synthesizer allowed it to punch well above its weight, delivering gaming experiences that remain iconic even decades later. Despite the rapid advancement of technology, the Super Nintendo continues to inspire nostalgia and admiration among gamers, and its games are still being played and enjoyed today. The lessons that the Super Nintendo taught us about design, innovation, and the marriage of hardware and software continue to echo throughout the gaming industry, and that's why it will always be remembered as one of the greatest consoles in history.